Hi everybody, my name is Jithin P. I'm a faculty of Department of Mechanical Engineering, Rajagiri School of Engineering Technology, affiliated to Kerala Technological University. In this audio presentation, I will be discussing on torsional vibrations. This is actually a sixth module topic of the course ME304 Dynamics of Machinery. This course is offered for 6th semester mechanical engineering students. So let's move to this presentation. Torsional vibration is angular vibration of an object, commonly a shaft along its axis of rotation. For a free torsional vibration, we just give an initial angular displacement to the shaft and it is then released. It starts vibration. That is, we are giving initial twisting to the shaft and it is released. It starts vibrating. This is what is called free torsional vibration. Torsional vibration is often a concern in power transmission systems using rotating shafts or couplings, where it can cause failures if torsional vibration is not controlled.
Free undamped torsional vibration system. So there are two keywords. Undamped vibration means that there is no damper in the system, and free vibration. Free vibration means that we are giving an initial displacement to the system and system starts vibrating, or we are giving an initial excitation and system starts vibrating. We are not applying the force or excitation again after the system had started vibration. So the system, such vibration system is called free vibration, and the frequency system is called natural frequency system. Now we will derive equation of motion for a single rotor system which is undamped, which is undergoing a torsional vibration. So this is a figure which shows a single rotor system. There will be a shaft. To that shaft a rotor is attached. Unlike the longitudinal vibration systems, which consists of a spring and a mass, it will have a linear motion. But in this case, we are giving an angular deflection to the rotor for starting the vibration. So the shaft will prevent rotor to move from its mean position. The shaft has its torsional stiffness. It is that stiffness which prevent the motion of the rotor from its mean position. Torsional stiffness is equal to the torque required to give a unit deflection to the shaft. In longitudinal vibration, we have discussed about spring stiffness. Spring stiffness is the force required to provide a unit linear displacement for the spring. Here, it is torsional stiffness of the shaft. Shaft is acting as a spring in this case. So the stiffness of the shaft, or the torsional stiffness of the shaft, is the torque required to provide a unit angular deflection for the shaft. So it is represented by the notation Kt, which is the torsional stiffness of the shaft. So Kt is equal to T by theta, torque required to give a unit angular deflection to the shaft. So it is this torsional stiffness which will be helping the system to restore to its mean position, or it is this resisting force which will prevent the rotor to displace from its mean position. Let I is the mass moment of inertia of the rotor, d is the diameter of the shaft to which the rotor is attached, and j is the polar moment of inertia of the shaft. For a shaft having a circular cross section, polar moment of inertia j equal to pi d raised to 4 by 32. Theta is the angular displacement which we are giving initially to the rotor. Theta dot is the angular velocity, which is d theta by dt, or it is equal to omega. Omega is what is represented by as theta dot. And theta double dot is angular acceleration, which is d square theta by dt square, or it is alpha, what is represented as theta double dot. So for the system to start torsional vibration, we are initially giving a angular displacement to the rotor. Say let the angular displacement given is in the clockwise direction when it is viewed from the top. So from the mean position, we are rotating the rotor in the clockwise direction. That is the applied torque. So the shaft will resist that motion, and the resisting torque is K into Kt into theta. We have the equation Kt is equal to T into theta. This is the torsional stiffness of the shaft. So the resisting torque T is equal to Kt into theta. So this is that resisting torque, you can see here. So this is the applied torque or the applied moment, and this is the resisting torque. And this I theta double dot is actually the inertial torque. We are representing inertial torque also with the system. So I theta double dot or I alpha is actually the inertial torque. So inertial torque is in the direction opposite to the applied torque. So applied torque, if the applied torque is in the clockwise direction, inertial torque will be in the counterclockwise direction. And the resisting torque will be also in the counterclockwise direction because it is the torque for resisting the angular deflection theta provided by the shaft having a torsion stiffness Kt. So inertial torque, which is represented here in counterclockwise direction, is negative of the accelerating torque. So negative of I alpha or I theta double dot. Restoring torque, that is the torque or the resisting torque provided by the shaft, which prevents the rotor from rotating in clockwise direction. So the resisting torque is Kt into theta. The negative sign indicates that the resisting torque is also, the restoring torque is also acting in the direction opposite to the applied torque. Now according to D'Alembert's principle, for a system having linear, for a system undergoing linear motion, we know that rate of change of linear momentum is equal to net force acting on system. That is a Newton's second law. So D'Alembert's principle represents Newton's second law in a static format. That is a net force acting on system plus the inertial force acting on system is equal to 0, or in dynamic equilibrium, that is equal to 0. So here we are considering a system which is undergoing an angular deflection. So Newton's second law can be stated as a rate of change of angular momentum of the system is equal to the net torque acting on system. So by D'Alembert's principle, we can represent the Newton's second law as for dynamic equilibrium, the sum of all the restoring torque and the inertial torque of the system must be 0. That is, sum of all the restoring torque, that is Kt into theta. If there is only a shaft which provides a torsion stiffness, which has a torsion stiffness Kt, it will give a restoring torque Kt into theta. Sum of the restoring torque plus the inertial torque I theta double dot is equal to 0. So sum of the restoring torque and the inertial torque are in dynamic equilibrium. So this is the representation of the Newton's second law according to D'Alembert's principle. So you can represent that equation like this also: theta double dot plus Kt by I into theta equal to 0. We have derived according to Rayleigh's method that general equation for a system which is moving, which is having a longitudinal vibration is mx double dot plus kx is equal to 0, or in the other way, x double dot plus k by m into x is equal to 0. And also we proved that k by m is actually the natural frequency, square of the natural frequency, omega n square. Here, instead of k by m, this is k by I. Instead of mass, it is the moment of inertia, I. So k by I actually represents the angular velocity, that is square of angular velocity of a system which is undergoing torsional vibration. So the natural frequency omega n will be equal to root of k by I. We found that natural frequency torsional vibration of a single rotor system is omega n is equal to root k by I, kt by I. Kt is the torsion stiffness of the shaft, I is the moment of inertia of the rotor to which the shaft is attached. And we also know that equation T by J equal to G theta by M. We know this expression. Torsion stiffness shaft is actually the torque required to provide unit angular deflection for the shaft. T by theta is actually our torsion stiffness. So you can represent T by theta as Gj by L equal to Kt, where G is the rigidity modulus of the shaft material. In some textbooks it is represented as C, so you can use Cj by L also for representing the torsion stiffness Kt. So omega m, we now have the equation root Kt by I, which is equal to root Gj by L divided by I, which is equal to root Gj by L into I. So this is our equation for natural frequency of torsional vibration for a single rotor system. Only one rotor is attached to a shaft and the shaft is fixed at the other end. So natural frequency in hertz, we can convert natural frequency omega, that is in radians per second, we can convert that to hertz by multiplying it with 1 by 2 pi. 1 by 2 pi into omega n is Fn, which is 1 by 2 pi root Gj by L into I. So this expression is in hertz. We will get the frequency in hertz. 1 hertz, we know that it is 1 cycle per second. So natural frequency in hertz is 1 by 2 pi root Gj by Li. So this is the expression for natural frequency of torsional vibration of a single rotor system.
Now we will do a problem related to torsional vibration of system in single rotor system. A flywheel is mounted on a vertical shaft as shown in the figure below. Both ends of the shaft are fixed and its diameter is 50 mm. The flywheel has a mass of 50 kg and its radius of gyration is 0.5 meter. Find the natural frequency of torsional vibration if the modulus of rigidity of the shaft material is 84 into 10 raised to 9 Newton per meter square. So our system consists of two shafts. First shaft is of length 0.9 meter, another shaft which have length 0.6 meter. A flywheel is attached in between these shaft. You can refer the figure. Now, before solving this problem, we need to discuss one concept. You might have heard this concept earlier. It is actually for how we can find out the equivalent stiffness of a spring arranged in a system. Okay, so our vibrating system consists of springs. Spring is actually an element in a vibrating system. So springs which are arranged in series, for finding out the equivalent stiffness provided by the spring which is arranged in series, we can calculate it by using the equation 1 by Ke. Ke is actually the equivalent stiffness of the spring, which is equal to 1 by K1 plus 1 by K2. So Ke is equal to K1 into K2 by K1 plus K2. Now if the springs are arranged in parallel, the equivalent stiffness of the spring in that system can be calculated by Ke equal to K1 plus K2. Now why I have discussed this concept is that our system is also a set of spring and a mass arrangement. We can represent the system problem, our problem figure, as shown in the figure below. You can see here the shaft which is lying above the rotor, that is 0.9 meter length shaft, that is actually represented by the spring, and the shaft which is of 0.6 meter, that is represented by the spring here Kt2, having stiffness Kt2, and the rotor in between the shaft is represented by this. So this is actually a system which is equivalent to our problem figure. So this system or this arrangement of spring is also equivalent to a parallel arrangement. You can see this is equivalent to the parallel arrangement of the spring. That is, for finding the equivalent stiffness in this system Kt1 plus Kt2, having spring stiffness Kt1 and Kt2, we can find that equivalent stiffness by using the equation Ke equal to Kt1 plus Kt2. Why I am representing the above problem figure in this format is that our shaft is actually acting as a spring. It will try to prevent the twisting which is provided by the rotor, which is due to the torque applied on the rotor. So our shaft will try to prevent the twisting. So both these shafts will act as a spring. It will try to prevent the twisting in the shaft. So these two shafts of length 0.9 meter and 0.6 meter is represented by spring having stiffness Kt1 and Kt2, and in the middle there is a rotor. So the equivalent stiffness of this system is same as that of the equivalent stiffness of a parallel system, that is springs arranged in parallel condition. Then its value is Ke equal to Kt1 plus Kt2. So the data given in the problem is diameter of the shaft 0.05 meter, mass of the rotor 500 kilogram, stiffness of the radius of gyration of the rotor 0.5 meter, And the rigidity modulus of the shaft material is 84 × 10 raised to 9 Newton per meter square. Rigidity modulus can be represented either by notation C or capital G. The polar moment of inertia of shaft can be found out by the equation pi d raised to 4 by 32. That is polar moment of inertia of a shaft having circular cross section. That you might have studied in earlier semesters. Torsional stiffness of the shaft of length L1. L1 is 0.9 meter. Okay, so the torsional stiffness of the shaft is found out by equation Cj by L1. C is the rigidity modulus, J is the polar moment of inertia of the shaft. Both the shaft will have, that is a shaft with the length L1 and shaft with the length L2. Both will have the same polar moment of inertia because both have the same diameter. And now we have found out torsional stiffness of the shaft for length L1. Similarly, the torsional stiffness shaft having length L2, that is 0.6 meter, shaft with length 0.6 meter, it has a stiffness Cj by L2, which is equal to 84 × 10 raised to 3 Newton meter. Now to find the net effective stiffness of the shaft, which is equal to K equal to KT1 plus KT2. We should add it because the arrangement which we have shown in the previous slide is of that of the parallel spring arrangement. So the equivalent stiffness will be sum total of the stiffness of the each shaft. So the equivalent stiffness value is 140 × 10 raised to 3 Newton meter. So the mass moment ratio of the flywheel, I equal to mk square. Mass of the flywheel is 500 kilogram. K is the radius of gyration of flywheel, which is 0.5 meter, and we can find out the mass moment ratio of flywheel. Now finally we will find out the natural frequency of the torsional vibration of this system given, which is Fn equal to 1 by 2 pi root Ke by I. K is the equivalent stiffness which we have calculated. It is equal to 140 × 10 raised to 3. I is the moment of inertia of the shaft. So 1 by 2 pi root 140 × 10 raised to 3 divided by 125. The natural frequency value is 5.32 hertz.
References for the session is Theory of Machines by S.S. Jithin, Mechanical Vibrations by VPC, Mechanical Vibrations and Industrial Noise Control by S.H. Energy. The remaining part of the session will be continued in the presentation named ME304 DOR, torsional vibration of 2 and 3 rotor system, in which we will be discussing about the derivation of natural frequency of 2 and 3 rotor systems. Thank you.